All right, it's recording, I think.
Awesome.
So, I mean, this is just like a brief overview of computational fluid dynamics.
Mhm.
But before we get to the computer aided stuff, there's a lot we can do with just pen and paper, which is important and doable and does not require you learning too much software or think about too many vortices. So the first formula you should be aware of is the lift formula, um, which includes something called the dynamic pressure, which is half rho v squared times CL times area. And that's equal to our lift force. So the lift force is in newtons. Oops. We've got in here something that you'll see a lot, which is half times the density times the velocity squared. That pops up in all sorts of fluids formulas. The lift coefficient doesn't have a unit, and it's pretty much a factor that says how lifty the foil is. You know, a flat plate might have quite a low coefficient, and then a really super cool foil might have a high one. And area is the area looking at the top from the top. It's the plan form area, so not the surface area. Drag, our drag, is exactly the same thing, except we're using a drag coefficient. Okay, now why are these formulas important? Because on the moth, we know it's going to weigh 100 kilograms times gravity. Say gravity is 10. So therefore, we know L has to equal 1,000. So you already have one known here. And the rest, well, the rest we have to figure out to design our foil. The density of water we know. CL and area we get to play with, and velocity is kind of an independent variable, like time, because we're not going to have a foil that delivers results in all wind ranges.
Sorry, can I just quickly ask, do you usually work in like standard SI units? Because there's been a couple of situations where I've done some sort of fluid dynamics experiment in physics, and we have to deal with some really retarded units that I've never heard of, like marks or something, and blah, blah, blah. Like,
Sure. So I don't think it's a great adjective, but we can use any units we want that are consistent. We definitely try and use SI as much as possible.
Okay. Good.
Yeah, but you know, velocity you could do velocity in feet per second if you wanted to, which would make area also in feet, and then your lift force would be pounds per, I don't know, your pound force.
Yeah.
So as long as it's consistent, it will work. But yeah, definitely at our club, we're trying to use SI as much as possible.
Cool.
So I want to give you.
I had a question.
Oh, another one?
Yeah, he put it into the chat, I think.
Oh, great. Can someone read that for me?
He said plan, form, surface area, not wetted surface area or frontal surface area. And then he said, actually, no, I get what you're saying. Plan as in lift.
Yeah, that is a good question. I mean, honestly, it's probably doesn't make a large difference because the difference in area, here's the first test. You know, the area looking down here, the area looking down is not much different from the actual wetted area that Alex pointed to. It's only really that much different. But yeah, I think that's just a convenience thing from back in the day. So let's have a closer look at the CL, because that's really the only unknown in terms of that's really the only fluids question here, right? We could all make up a random area and measure it up in CAD or whatever. So CL is really what we're trying to find using this software. So we can definitely use XFLR5, we could use XFoil, we could use fancy stuff like the foil team is using, which is called RANS, and will take a few hours. We can go to a place called XFoil Tools, Airfoil Tools, I mean. And Airfoil Tools just uses XFoil, the X4 engine. So same thing that we're going to be using. And you can search for a foil. So NACA is the name, is the National Aeronautics something something. It's the precursor to NASA. And they have a whole bunch of foils that they came up with initially. Annotate, erase. And close annotate. So here they give you the geometry of the NACA foil, which is important, obviously, if you're going to plot it or send it to be machined. And they show you a few plots at different speeds of the graph of the various properties of the foil. So there's a few things we need to define still. The first of which, let's not go so low. Let's go here. You'll get a better plot. First of which is this thing called the Reynolds number. You'll see it everywhere. The Reynolds number is just non-dimensional. What is it? It's the non-dimensional inertial forces divided by the viscous forces, which doesn't actually sound like it's that helpful. But once you see the formula, you'll see. God damn it. Reynolds number is equal to, you've got your some sort of length times some sort of velocity divided by the kinematic viscosity, which is nu. Yes. We'll just make our velocities capital. So this is our length, where L is length, V is velocity, and Greek nu is kinematic viscosity. Pretty much all I want you to get from that formula is that the higher the Reynolds number, the higher the velocity. We've non-dimensionalized it, so it doesn't actually have units, and that can help us deal with air at, it doesn't matter if we're looking at air at ground level or water or air at supersonic speeds. It's just kind of makes it all non-dimensional, and we can make fair comparisons. But essentially, it's your velocity. It's your velocity. So when I'm looking here at different Reynolds number, you can just think about faster flow. First thing you'll notice, we're looking at this right-hand plot, which is what we wanted to find, our CL. Alpha is our angle of attack. So what angle is the flow coming from? That's our alpha. It can be measured in degrees. You'll notice that it's pretty much a linear line for the first little bit. Let's say to 10 degrees from 0. That's a fairly linear line, especially for lazy engineers. So the greatest approximation you can use, how do I do this, mouse? I think, no, curved line, is that CL is equal to 0.11 times alpha. Yep, so here we see, you get a CL of 1 at alpha equals 10. So that's not a bad approximation. Pardon. But let's say drag is really the more difficult thing to estimate, but this will get you home. If you're doing fluid calculations at the back of the envelope, sorry, I did the wrong one. This formula will help you out a lot. Now, if you were to put a flap on it, flap on the foil, you don't get this nice relationship anymore. It depends a lot about the flap size and the foil. So that's when you start having to use these CFD software, which we can do. They're all designed to do that because these are the problems that aeronautic companies have had for a very long time. Tate, can you tell me why do we use flaps?
So sorry?
Can you tell me why we use flaps?
Because it's a real pain to change the angle.
Yeah, absolutely. It's hard to change the overall angle of attack.
And you can get a lot finer tune with a flap too.
Nice one. Yep. Yeah, ideally, you would probably just morph the foil. You wouldn't even change the angle of attack. You would just somehow wiggle the shape of it until you were happy in all sorts of ways. Or as you say, maybe you could change the overall angle of attack. We don't have that luxury in reality. So a flap is a quick and dirty way to increase the lift force. It can be a bit blunt, like looking at it this way, the way I've drawn it, the flow will be coming here and have to make a big change in its direction. So, it introduces a fair amount of drag. and the flow might separate here. It won't be able to follow that. Cool. So the other thing that airfoil tools will give you is your drag coefficient versus alpha. Oh, that's annoying. Is there an erase all? No. Okay, your drag coefficient versus alpha, you'll notice it's symmetrical, about 0 angle of attack. That's because the foil that we picked, this NACA foil, is symmetrical. It looks like a teardrop. Ooh, did not draw it symmetrical. Okay, so if the foil's symmetrical, then the drag is symmetrical, no matter where the wind is, the apparent flow is coming from, which is nice. And then let's show you what a NACA 2412 looks like. So this is a non-symmetrical foil. You'll notice also in aeronautics, they keep pointing, the planes point to the left, but boats point to the right. Boats point to the right, which is why I keep drawing the foils the other way. Yeah, so this is an asymmetrical foil, and we have asymmetrical drag. Even if we look at these plots of the lift plots though, you'll still see it's pretty much a straight line. But it does go further. What do I mean by it goes further? So this area of the plot, do you know what? Can you explain what's happening here, Mahima?
All I can say is turbulence.
Yeah.
Or like you just sort of reached the edge of, yeah, I don't know. Yeah, that's all I can think of is like you've got turbulent flow. Cool.
So this is this arrow here that I've drawn is our alpha, right? So we're tilting the wing more and more. Alpha is coming more and more from below. And what we're noticing is that as you increase the alpha past about 14 degrees, the lift starts to reduce, right? This is called stall. And you're right that, well, it's not the turbulence in the free air that's increasing, but certainly there will be vortices being shed off the foil at 14 degrees. And rather than the flow, let me pick a different color. Rather than the flow coming and hugging the foil beautifully, it will come in and kind of be shed off some point in the foil. And that is called separation, and for sure there'll be very turbulent air in here. So that's our stall. You'll notice at stall, scroll down.
If that's stall, then what's happening on the other end of the graph? Because it's doing the same thing but in reverse, right?
Yeah, it is doing that.
Just when you're not getting enough airflow, like your angle of attack is like yeah, I don't know how to physically interpret what the other end of the graph is doing.
The other end is the exact same thing. Now we've picked an unsymmetrical foil, so
Right.
it's not quite the same angle. Here it's
Mm.
like 14 and here it's 9.
Right.
But if we picked a symmetrical foil,
Are those negative numbers?
yep, those are negative numbers. What that is saying is, come on, help me out, Zoom, is that the flow is coming here from the top.
Right.
Rather than here from the bottom.
Yeah.
Well, this is from the bottom, it's like 14 degrees until stall, and from the top, it's like 10 degrees until stall. Yep, so it's only because it's an asymmetrical foil that we have these differences between 10 and 14. If it was symmetrical, then it would be the exact same number. Really, you can just, the plot has moved to the right a little bit, if that makes any sense. Like if I was to recreate this plot, like that, you know, centered about 0, then we would have both foils would stall at the same symmetrical point. So the last thing I want to show you on airfoil tools is we have these drag curves too, which are nice to look at. Let me exit that again. So we have the drag versus angle of attack, which kind of looks like a bucket. And we have something called the lift to drag versus alpha. So this ratio, can you talk me through it, Tate? If you have a high lift to drag ratio, what does that mean?
Bear with me, I'm still waking up.
Sure.
That's kind of showing like your sort of like rate of return for increasing the angle almost. Is that right? It's like once you increase it past like 6-7 degrees, you're getting diminishing returns.
Yeah, absolutely. I mean, there's a strong
you're still
peak here.
your lift, but you're increasing lift at the expense of much higher drag.
Yeah. Alex, by the way, I'm the only reason I'm not calling on you is because we haven't managed to hear you via your mic yet. Feel free to chime in. You just put something in the cool. Yeah, if you get it working, let us know. So you can think of the lift to drag ratio as kind of your efficiency for your foil.
Yeah, because you have to balance lift to drag, right, to get flight.
Absolutely. So if we actually define the lift properly, lift is actually the force perpendicular to the free stream direction. So if this is our alpha, lift is actually, you define it perpendicular to alpha. And then our drag is alongside alpha. So this is our lift and this is our drag. So you can definitely see, you know, then you could break this down, do some trigonometry if you cared to. You know, that the overall force is, say here, just being T being, you know, T squared being L squared plus D squared using Pythagoras. And then you could break that force into, you know, your vertical force, which I've not done myself much favors in how close I've drawn these angles, but you can do like, you know, your vertical force and your, let me try that one again. Your vertical force and I don't know what I'd call this. Your drag in the direction of movement force. So we want a foil that just creates loads and loads of lift and minimal drag, right? That would be the dream. You want high CL and you want a low drag. So you want a high CL CD ratio. And then this changes with angle of attack. So you wouldn't want to use this foil past 6 degrees. You might want to use it from, what is this, -2 till 6 degrees. If this was a symmetrical foil, then it would, it would start at 0. But we're dealing with a funky foil currently on screen. So how does everyone feel about drag and lift? We starting to get a sense for it?
Yeah.
Awesome. Is it time to whip out some software?
Yeah, that would be good.
Let's do it.
In about half an hour. So, yeah.
Cool. Now, so this is XFLR 5. First thing you should do is go to the direct foil design tab or control window. On screen, you'll see some weird foil and you can play with it if you want. The better way to do that is foil. Let's put in a NACA foil. So this is, again, those pre-made foils from NASA, well, what used to be NASA. And we'll start out with the 0012, which is a stock standard foil. We actually have it on the boat as well. I can't delete this other one. Why can't I delete it? Manage foils? No? Okay, we'll just leave.
Bottom right, there's like a show column.
Oh, thank you very much.
Cool.
And we can also probably change the color so it's easier to see on the screen. So yeah, we actually have this foil for our dagger board. It's something, sorry, for our rudder, and potentially our dagger board too. This is a symmetrical foil, so it needs to work on both tacks. Has everyone managed to put in one of these guys? So in the direct foil design page, I went to foil. I scrolled down and I found NACA foils. Here you'll see all sorts of tools that you can do to change your foil. We can set a flap and we'll do that later. But just so you can look at it, I've put a little flap here. Flap on my friend. Okay, so the next step in XFLR 5 is you'll go to a direct analysis. you should see your foil coming up in this screen here. And you might have this floating around somewhere. I like to, what do you call it when you put a module out to the side? Snap. I like to snap it to the right-hand side. Cool. And the first thing we're going to be doing is an analysis. So F6, and we have this foil. So right now, it's kind of already given you an automatic name for it. I wouldn't worry about analysis type for now. It's just looking at different ways to define the flow. Type 1 is great for us. It's using the Reynolds number like we came up with before. And the Mach number, which is kind of irrelevant for our velocities. You can just leave that at 0. The Mach number, is the speed of sound. The speed of sound that our foil will be going through the water. And when you get to maybe Mach 0.3, when you're going 100 meters a second in air, which is 200 knots and what's that, 360 kilometers an hour, then air starts doing funky stuff. But we're not going 360 kilometers an hour, so we can leave that at 0. And Mach number. Let's find out on what is an appropriate Reynolds number. Okay, our Reynolds number is V times some length divided by nu. What is the length of our foil? I think in XFLR it's 1, so that's easy. And what should we do, guys? Should we do water or air?
Whatever is simpler.
Can't just search water. You need to search for water kinematic. Viscosity. Which I'm pretty sure is it's 10 to the minus 3 divided by rho. This is actually, Engineer's Edge has a good page for this. I'm just not on it.
I vaguely remember it's like 8.9 times 10 to the minus 4 Pascal seconds.
Oh, yeah.
I don't know why I remember that.
Again, this is not the right Engineer's Edge page. Oh, water. This one? There you go. That's the page I go to all the time. So this changes with temperature a little bit. But 20 degrees, we have basically just 1 to the -6 times 10 to the -6. Apologies, that took a little bit to find. So we have, this is 10 to the -6. And then what's our boat speed? Should we go for just standard 10 knots or 20 knots? 20 knots is roughly 10 meters a second. So we have here 10 times 1 times 10 to the -6 is equal to oh, this is okay. Well, I mean that is equal to 10 million, but it's a mistake here because our length, our foil is not 1 meter long. Our foil is 0.1 meters long. So here comes the beauty of the Reynolds number. Our foil is 0.1 meters long. So on our boat, the Reynolds number is 1 million. And so when XFLR uses a Reynolds number of 1 million, they might change the length. You know, they might put in a length of 1, but they'll have to change the velocity to correspondingly. And so the fluid characteristics will be the same. Hey, Alex. Alex2 is trying to join the call. Hey, Alex. Alex2. Is this trying to get your mic working?
Oh, hello.
Yes. Awesome. Good to have you.
Oh, great to be here.
Any questions you want to ask?
Not yet.
Cool, man. Yeah, okay. So we figured out our Reynolds number. It's 1 million. Let's leave everything else the same. Push go. That didn't look like it actually accepted my million. Are you really going to ask me to put in a comma in the right place? Awesome. So on my screen, I've got my NACA foil here. They've found my analysis. And now I get to see what happens when I put an angle of attack of 5, analyze. Has everyone managed to get to this point?
No, my screen is just blank.
Uh-huh. So did you create a new project?
Yeah, I've got, so I don't have the picture of the foil underneath showing, but I've got the NACA 0012 showing up underneath the graphs and stuff.
Oh, are you, try click these buttons here. There's a polar view, F8, and there's a operation point view, F5.
Oh, yeah. Okay, now I've got it. Yeah, now I've got the same thing as you now.
Awesome. So you can run, you know, a single point, or it'll let you do a sequence from 0 until, let's say, 10. Let's go at 1 degree increment so our screen doesn't get too busy. And now we've got results from 0 all the way to 10. This graph here that we're seeing is the pressure along the foil. So if I was to move the foil, that's annoying. If I was to move the foil and zoom it in, so it's roughly the same size. This is the foil, the pressure going past the foil. So at the beginning, you can think of this negative pressure as lift. Well, all this pressure is lift. But we're looking, the top line here is the pressure along the top surface of the foil. And the bottom line is the pressure on the bottom surface of the foil. So you can see we have a positive pressure on the bottom, which is pushing the foil up. We have a small force pushing the foil up, and we have a large force sucking the pressure up, a large negative pressure that's sucking the pressure, the foil up. There is actually a setting in Xfoil to display these arrows, these vectors. Maybe right click. Current foil. I don't know. Not important right now. Cool. So that's very good. We've just got our pressure. It's interesting for a few points, but mostly what you'll see is that at low angles of attack, you get the smooth line here. And then as you start to increase the angle of attack, you get the spike forming right at the front. And that spike is not fast. If this was an airplane, you'll get like sonic shockwaves forming. If you were a boat, you'd get cavitation happening at these things, which is why generally for our foils that are creating lift, such as our horizontal foils, we're trying to avoid these sorts of looking plots.
Can you explain what cavitation means? Because I understand it from a plane perspective, but to be honest, not really. So can you just explain what's happening in a bit more detail at this initial peak?
Yeah, absolutely. So we can just go back to this, I guess. So you'll see that the properties of water are very dependent on temperature. So, you know, there's a 0.3 down here at 100 and 1.8 here. I don't know what percentage that is, but you know, it's like there's a really big difference in water properties between the temperatures. And one of those differences is the temperature at which water boils. You might have heard that when you're on the Himalayas, when you're climbing the Himalayas, water will boil at like 60 degrees. Because the pressure there is reduced. So the exact same thing is happening here. This -5 is, okay, be careful about double clicking. This -5 is saying that the pressure here is, got a chat. Oh yeah. What have you got for us, Tate? Oh yeah, this is a great video. To actually see the cavitation happening.
2 minutes 30 is where the action starts. About 2 minutes in.
But just before we get there, so that -5 is showing a really negative pressure. So it's I told you you'd see this again, but that half rho v squared, which is, I mean, you can just call it the dynamic pressure or Q. You'll know what max Q is. Yeah. So that's the max Q. Well, that is Q. So here it's like it's -5. So it's the like atmospheric pressure plus foil pressure, I think divided by Q. So you're saying that the pressure here is like -5 times the atmospheric pressure and foil pressure. Which is to say, like, we're not making a vacuum, but we are at a very low atmospheric pressure. And just like in the Himalayas, when you have a very low pressure, water starts to boil at lower temperatures. And you can even get the pressures so low that water starts to boil at like 20 degrees.
Wow.
So what you'll see in this video that Tate posted, which is really cool, is phones in front of other phones. But you'll see also, Jesus, yeah, this bubble that's forming here is water vapor. Like this is all water that's boiling.
At the leading edge?
Yeah, at the leading edge of the foil. And it's also spreading in a particular pattern, just where the low pressure is, the lowest pressure is. But the flow is now starting to slow down, which is why the cavitation is reducing. Yeah, but it's just water boiling, really. It's water boiling at 20 degrees, which is really cool. The reason why it's bad is just it makes more drag, pretty much. Right. It also makes like the foils vibrate a bit, and it can help you lose control.
Yeah.
Yeah. So generally, we don't like these big spikes. The other view to look in XFLR5 is your polar view. Now you'll only see a polar view once you've got a lot of points calculated already. Is because and this is going to start looking familiar compared to airfoil tools, because we have here a lift versus alpha. We have CL versus CD versus alpha. We have some other ones. I think you can just create whatever graphs you like. Where's graph 6? 4 graphs. And can I make this graph a different graph? I can. So we can have our CD versus alpha in here, which is that first half of that bucket. If we go and we put in a new sequence of -10 to 10, you'll see that bucket is symmetrical. I don't know why this graph is so weird. And you'll see our almost linear line here that we were noting before. If we keep going, let's see how similar it is. We thought that 14, I think, from memory, was when stall started to happen. And you'll see it's pretty much the same, which makes sense because they use the same solver. So it wouldn't be a good sign if they didn't stall at the same place. So that's great. So has everyone managed to get somewhere this far on their screens?
Yeah.
Cool. I mean, that's kind of the main point. We can go back to our foil, and we can try and add a trailing edge flat, maybe. That might be interesting. Let's go trailing edge. Let's go 5 degrees down and make it full 30% of the foil, which is close to what Krishna is working with. Apply. Okay. Let's call it with flap of 5. Cool. So we have a new foil. That is orange. And this new foil, we can analyze it by selecting the new foil. We haven't run anything for it, so we need to define an analysis, which is F6. We'll keep it at 1 million. Press OK and run the exact number of points that we did for the other one. And you'll see, I wonder if we can compare the two foils at the same time. That would be interesting. Well, I guess it is doing that for us in the polar view. So you can see that when we put a flap on, the foil becomes asymmetrical, right? And it actually starts to create lift at, at a negative angle of attack, which is kind of weird to think about. That even though the flow is coming from the top, it will still create lift. And you'll see the flap is seriously changing the pressure distribution. But going back to this view, you'll see that it just creates a lot more lift, right? Having a flap on creates more lift. So if we set the boat up at whatever, like a 2-degree general angle of attack, and we move the flap, we can suddenly jump up to as if we changed the entire foil up to 6 degrees. So that's nice.
Sorry, just to be clear, so the two lines, like the one line is the original one we had without the flap, and then the other orange one is with the whole, it's like the whole system together, right? Like with the flap attached. It's not just the flap on its own.
Correct.
Okay.
Yeah. Yeah, this foil has, it's the entire foil with the flap. We can define another one. Set flap at 10 degrees, and you'll see it's pretty much linear. F10. And do we have any requests for this color? How about green?
Pink.
Oh, pink. Yeah, shit, yeah. Go back to our analysis. We've got a new foil, so we need to run an analysis for it. We're keeping our Reynolds number the same, and we can just run the same points as before, and you'll see it's pretty much just linear. They're introducing more drag, so you can see that each time we've changed the flap, we've gotten more drag, so you don't get this extra lift for free. And that's sort of a game you can start playing between. And I did an analysis on this on the controls page a few months ago of what's the trade-off between the overall angle of the attack of the foil and the different flap sizes. Another way you can run these plots is you might say to yourself, hey, I know my CL, it's 1,000, and I know everything else, so I'm going to say that I do. Let's figure out what CL we want. So CL is equal to the lift divided by this whole thing. You know, so we can work out backwards. What foil do I need to choose to make my boat fly? So you might be interested, you might solve this equation, which we can do by hand. We might say something like, we might say something like 1,000. We'll make that 2,000, get rid of this half, is equal to 1,000, which is the density of water times 10 meters a second squared, which is 100. Gosh, I don't remember what area. We have, I think, maybe 0.04. Who's got a calculator nearby?
Yep.
I guess we can simplify this somewhat. That can be 1 and that can be 2. And that is 4. So it's 2 divided by 4. So we need a CL of half, roughly.
Yep.
Look at that. Math still works. So great. So let's look for a CL of 4. So back here, we can choose our different foils. Say we're going to our non-flapped friend here, the NACA 0012, old trusty. We can put in our, rather than using an angle of attack, we can say, hey, we think we're going to need a range between 0.2 and 0.6 CL. Maybe you can climb up there at 0.5 CL increments. Let's analyze it. Right, so it's come up with, what does it come up with? Oh, that's cool. Here's the wind. Here's the pressure I was talking about before.
Ooh.
Fancy. Get rid of the animate. Yeah, here are those arrows I was pointing at before. You get suction at the nose, which you can see on the graph, and a very small positive pressure regardless. So maybe I just need to delete the other foils. Current polar, delete. So let's just go 0 to 1. .05. Oh, I think that was where the mistake was. It needed to be 0.5 increments. What have you got for me? Right, so it's come up with all sorts of weird angles of attack to come up with the correct CL. So that's great. We can see that it's annoying that you have to pick it out this way though. Does it show it nicely here? Maybe not. Maybe it's something that, you know, in this program, looking, oh yeah, at our yellow line, you just export the file to Excel and you interpolate and you say, okay, I needed 0.4. So that's 2 point something degrees, 2.3. So our foil can fly at, you know, this angle of attack, 2.3 degrees, and our boat will be flying. Pardon me. If we did the same thing with the flapped foil, what would happen? If we did the same thing with the flat foil, we needed 0.4 degrees. That would be like our 0 point something angle. So you'll see that if we've got our flap down at 5 degrees, we can get the exact same lift, which is what we need right now, which is 0.4 to be flying.
Yo, Toma.
Yeah, man.
So does that mean that our global airfoil is at 0 degrees, but our flap's at whatever, X?
That means, I wish I could go back because I ruined everything. That means our foil is at 0.2 degrees, and our flap is at 5, is what the orange line
Cool.
is
Thank you.
showing. Yep. Cool. So I think we'll leave it there in terms of like the software stuff. You can do like a full plane analysis, which you can define a little plane. And I don't know this well enough to, like, I have played with it a little bit, but a 1 meter wing. What is Z? I don't know. Yeah, you can actually create a full plane. My wing is not very long. My main wing. Oh, there it is. It's at the back. Which is nice because then they'll start looking at some 3D effects. All this stuff that we've done today, all this 2D analysis, does get changed a bit at 3D, but we won't cover 3D aerodynamics today because it gets super weird. That could be another day. Cool. I'll leave the class open to questions. The church. Does the congregation.
The Church of Education. No, this was awesome, man.
Cool. Yeah. If you've got questions, fire them at me. If you're, if you have a little project of a question, like, hey, would it be able to figure out this on the moth? Then let me or Krishna knows. He knows the software very well. Him and I actually use XFoil, which is...
It's like the command line version, eh?
Yeah, exactly. So it's got all the same stuff. I can create... Where is it? I can create my NACA 0012, which you can't see, but it's there.
Yeah.
For example, oops.
Just without the nice GUI.
Yeah, and we can create an operation point, and we can put in our Reynolds number of 1 million, and we can run an alpha sequence between -10 and 10 at 1 degree increments. I think. Anyway, it's all the same. The benefit to using XFoil is you can script it.
Yeah, definitely.
So you can very easily. Oh, there you go. That's all my distributions that I asked for. Yeah, so it's very much the same software. How do I exit? God damn it! There's this bug that like you can't if you highlight, if your mouse hovers over the graphics window, it will come to the foreground, which is very annoying.
Mm-hmm.
But do I go exit? No. Do I quit? I do quit.
Perfect.
Yeah, so you can script it, so it means you can go through a whole folder of foils really easily.
Yep.
the other thing that both software do, which I didn't talk about, is kind of going backwards. So before,
design.
remember I said, this pressure distribution is related to the geometry. And we don't really want a big spike here. So what you can do, which takes a lot more math and a lot more understanding, is you can actually create a pressure distribution that you want, feed it into these software, and it will come up with the foil shape.
Could you do a rough live demo of that? Or do you not trust yourself?
Let's give it a go. I don't trust myself is the quick answer. Let me erase. Yeah, this is just guessing at this point, especially in XFLR 5, not in XFoil.
Mm-hmm.
Come on, snap. Nah, mate. Oh, hello.
Oh.
Oh, this is this is a Q infinity versus XC plot. Okay, that's not what I wanted. See, I'm very used to thinking about pressures.
Yeah. Oh, good.
Well, let's see what happens if I do that. Execute. Must mark off target segment first. I don't know what that means, you see. Yep, sorry.
That's all good. But yeah, I can see, yeah. It just takes a bit more understanding to do something within sort of reasonable calculation.
Yeah. But that also lends itself really well to scripting things and trying out lots of different foils and different shapes. You can also do cool things like morphing foils. Sorry, that might be misleading. To blend between two foil shapes.
Oh, yep, like genetic breeding kind of thing.
Yeah, exactly. So you can be like, I kind of want the properties of this foil and the trailing edge, and this properties of this foil and the leading edge, and the software will
try and find a happy medium.
Yeah, exactly.
That's really cool.
So like I was saying, this is the, well, maybe I wasn't saying it enough. This is the quick and dirty CFD that we can use. And, within 1 minute, I can give you what the pressure distribution is and what the lift coefficients are, which is awesome. Unless you're creating brand new foils, you'll be able to find it on Airfoil Tools. And these are they're using XFoil, so it's already done the things for you. And you can read them off the graph or export them to Excel somehow. Details? Yeah, you can export it to Excel and interpolate to find all your solutions. The other form of CFD, which takes a few hours to calculate, is called the RANDs, which is what Krishna and I did for our master's degrees. But you can do it 4th year in engineering. And yeah, it's a 3D thing, and it calculates this giant mesh of points. It's just a more accurate and slower way to do it.
Sweet.
Cool. Let's leave it there.
Sounds good. Thanks for that, Timer.
You're welcome.
That's awesome.
We'll see you sometime. Bye.
Thanks, Omar.
See you, man.
See ya.